have Professor Mahn-Soo Choi from Korea University. Mahn-Soo is a frequent visitor of this university. He has come already 3 or 4 times, I think. And some of us have had the opportunity to have collaboration, long-term collaboration with him. In the framework of this collaboration, I visited his university for sabbatical last course. Mahn-Soo is an expert on quantum transport and nanoscience in general. And today he's going to speak, I think, about a very recent work he has done with new ideas on the superconductivity problem. He's staying all this week in the visitor's office of the last floor of the institute. So if anyone of you would like to talk to him until the end of the week, he's around. So, thank you.
Okay, muchas gracias, Rosa, David, Lorenz, por invitarme aquí. Y IFISC, what else? Well, I'm done. In Spanish, this is all I can say in Spanish. That's right, I understand the audience is quite general from several different fields, and I try my best to keep in general. But if you have any question, please don't hesitate and wait to just ask me a question. It's about something very simple idea how to test these Coulomb pairs. What are Coulomb pairs? It will be clear in a minute. Okay, before I start, this is kind of my duty, because recently I was appointed for the program coordinator of this institute, and we are strongly recruiting some young scientists. So it is an APCTP, Asia Pacific Center for Theoretical Physics. It's a kind of counterpart of ICTP in Trieste, Italy. So the purpose is, of course, quite clear: to promote the scientific activities in Asian countries. But of course, it's a quite international institute. Several years ago, we invited Peter Fulde from Mahn-Soo Institute to be president of this institute. So because of his amazing efforts, now the APCTP has been pretty much improved, and now the activities are very strong. So because of his part of the efforts, now the APCTP is now have a very strong support from the Max Planck Institute. For example, this junior research group activities are directly supported by Max Planck Institute. This junior research group is a kind of subgroup with senior postdocs. So if you, for example, if you are willing to spend some 5 years in Korea, then you are granted some fund to hire several postdocs and research funds and so on. And we also run some visiting scholars program, so you are very welcome. Please, if you have a chance, come over and share your information and expertise with young scientists at this institute. Currently, I'm trying to recruit at least one position for young scientists. Young scientists, by young scientists mean just after your PhD. So within 1 or 2 years, if you have a strong candidate, please let me know. And we are, especially in condensed matter physics. Okay, so much for advertisement. Let's go to the topic. Okay, superconductivity. Probably it is well known by phenomenon. It's conduction without any dissipation. So it is a quite noble state of electron matter, and still it remains as a mystery, especially the ITC superconductivity still is challenging for theoreticians. But at least some basic physics is known. For example, this superconductivity is known to be caused by pairing of these constituent electrons. Electrons, of course, are fermions, but these fermions, they make some pairs like this, and these pairs are called Cooper pairs, after some famous physicist, Cooper. And the Cooper pairs undergo some kind of condensation. That's what we understand. It undergoes a condensation, and because of the condensation, the whole macroscopic of the system is described by a single macroscopic wave function. So we don't need to describe all the microscopic details. We only describe by just a single big wave function. Yeah. So this is pretty much similar to Bose-Einstein condensation and superfluidity. Indeed, there are many superfluid and superconductors. They share many common properties, like of course dissipationness, and because of the macroscopic wave function, they have quantized vortices. And as I said, because of this wave function, macroscopic coherence, all in a big scale. But of course, these two systems, if you look at the details, the two systems are quite different. Superfluid is caused by the bosons and pretty much related to Bose-Einstein condensation. Of course, there is an interaction, and therefore it's not pure Bose-Einstein condensation, but essentially it is a Bose-Einstein condensation. But the superconductor is the constituent ingredient particles are fermions, and therefore it should not be a Bose-Einstein condensation. But anyway, they have pairing, and therefore it's also a kind of condensation. The question is this also, can we understand this condensation of Cooper pairs in terms of kind of Bose-Einstein condensation? So that's probably, that is quite tempting, right? So many people are tempted to understand superconductivity also in terms of kind of Bose-Einstein condensation, right? That was my motivation to start this work. Well, this question is quite simple. For example, the compact particles of even number of fermions is bosons, like a helium-4. Helium-4 is actually not a single particle. It consists of 4 particles, but all fermions. But still, because it's an even number of fermions, we can regard this as boson, right? At certain range of energy scales, of course. If the fermions, if you combine the odd number of fermions, of course, it's still fermion. Right? So Cooper pairs, it's a pair, just 2 particles, and therefore we may ask, Cooper pairs are bosons or fermions? Right? So that would be the question you may ask. Well, when I was very young child, probably not only me, so many Koreans, when they are quite young, they are asked this question, kind of trick question. So does a tadpole lay eggs in warm or cold water? So I was pretty young, and I was quite embarrassed because I never thought about it. Okay, so I answered probably in warm water, right? Because usually you can find these tadpoles in summer. So probably the tadpoles like warm water. Sorry?
What's the translation of tadpole?
Oh, tadpole. This baby form of the frog.
Okay.
So they swim, right? They have tails. Right. Okay. This is important to know that, so what tadpole is. So I was quite embarrassed. So I answered probably warm water, right? But actually, he doesn't care. So he has this little tail, and he pretty much like swimming rather than laying egg, right? Eggs are laid by frog, not tadpoles, of course. Right? So this question was wrong. Right? That was a trick, of course, right? So here as well, mathematically. So if you look at a little bit, take a look at this BCS state, which is condensates, which is believed to be described as condensate state of superconductivity, is formed by some creation of pairs. So this pair is called Cooper pair, and therefore we can regard this as a pair creation operator. So the question may be the question if the Cooper pair are bosons or fermions may be asked by this simple commutation relation. If this commutation relation is just one, then of course we can regard it boson. But obviously it's not one. So the answer is pretty much clear. It should not be boson, right? So the question was actually previous question was itself was wrong, because it was obvious it's not boson. The proper question would be how much of bosonic nature are Cooper pairs, these Cooper pairs have. So that's the question I want to ask, and I think using this Hanbury Brown and Twiss experiment, we can provide some quantitative measure of how much of this bosonic nature. Okay, so the outlines. So for
yeah, a good question. So you're saying that there is a transition between bosonic and fermionic behaviors? Continuous?
No.
When you ask how much of bosonic behavior, what do you mean by that?
No, so in the super
partially bosonic or something like this?
No, maybe so from the phenomena or so the properties, the phenomenological properties, we can say that probably the Cooper pairs behave something like a boson. It's not exact boson, but like bosons. But how much like? That's the question I'm going to ask.
So they have some properties of the bosons, but not all of them.
Right, right. Not exactly boson, of course, right? But probably quite similar to boson maybe, because the reduced phenomena are pretty much the same, right? Like the bosonic system. So many people expect that probably the Cooper pairs behave something to some extent like bosons. But then the question is how much can you regard?
Let me ask a very simple question.
Yeah.
What's wrong in defining bosons or fermions using the spin statistics connection theory? So depending of
if your composite particle is a really tight binding particle, that's enough. But in this case, as you
what you are asking is how much abound the state is the Cooper pair.
Yes.
Is that what you are asking?
right. Actually, it's not a bound state. Actually, this Cooper pairs is not a bound state. If in some limit they form indeed a bound state, and then it is really a Bose-Einstein condensation. That has been tested in cold atoms, changing the interactions between electrons, and they went to the limit where these electrons form really a bound state. In that limit, in certain energy range, of course, this commutation was satisfied completely, and it coincided with these spin statistics. But in this case, it's not possible. Any other question? Right. Okay. So then, here I propose that we can test to what extent we can regard these Cooper pairs as a bosons or completely not by means of this Hanbury Brown Twiss experiment. And we need some setups, so I will introduce you Hanbury Brown Twiss experiment, And because of the Cooper pairs, we need some special properties. Here I'm going to use some topological insulators, which has been discovered recently, and some another description of Cooper pairs in terms of undirect reflection. And then I'll put them together and then construct a setup for Hanbury Brown and Twiss experiment and give the result. Okay, Hanbury Brown Twiss experiment. Here I have a problem. I'm not an expert in quantum optics, but I know that here we have a pretty good group of quantum optics. So probably I suggest that some of you will cooperate instead of me. For example, Roberta, what do you think?
I do not even know the reference.
Okay. Well, okay. As I'm not an expert, so I keep the discussion minimum, right? There are two kinds of interparameters in the world: phase interparameter and time intensity parameter. Phase interparameter, the typical example is this. Michelson. Sorry. Thank you. Thank you very much. Michelson interferometer. That was the most common interferometer before Hanbury Brown Twiss experiment, but because of very sensitivity of this phase interference and decoherence, that technically it was quite limited. And then these guys, Hanbury Brown and Twiss, came up with a new idea with this intensity interferometer. It consists of two. They applied originally to the radio astronomy, not the light, visible light. So here they collect two signals. So from the star, the lights come in here, two antennas, incoherently. Right? So they collect them together and they get correlation. Right? So at that time it was quite surprising. So you have two independent sources of light. It's the electromagnetic wave, but still the experimental result showed you some interference effect. So it was quite amazing and surprising because you have two independent sources, but still they do interfere with each other. So that was quite at that time was puzzling, but anyway, so they developed this idea even through these optical lights. Okay, so to point out the relevance of this experiment to my setup, I'm going to point out just the essential point of this experiment. So what this experiment is equivalent. They made later to argue the people who are who are against them. They developed this tabletop experiment. This is equivalent to the previous experiment. So one light is come here, and one light is divided by this beam splitter, and one goes here and the other goes here. They make a correlation. So again, this is an intensity correlation. Okay. And this was fully described by this first semi-classically by Purcell and later fully by Glauber. And that was, I think, the start of the quantum optics. Am I right? Right. Okay. So, and he got the Nobel Prize for this achievement. Okay. So, the essential idea is that there are two things I want to point out. Here we have a beam of particles, in this case photons. So we make a measurement of the coincidence measurement of intensity at time t and the intensity at time t tau here. And I also point out that by Bain, in his textbook, that the intensity correlation between them is equivalent to measure the probability to find two particles spatially distributed particles at the same time. So this intensity correlation is related to the spatial correlation of two particles. So of course, these spatial correlations are different for fermions and bosons. Okay. There is another thing. So this effect is a true interference effect. This can be seen by taking a look at this thing. For example, these two particles, let's focus on these two particles. This real particle can go through here, and this particle goes through here. That's one possibility. Of course, there is another possibility, but this, instead of going through it, this particle goes down, and this particle goes through it. Right? There are two possibilities. But because these two particles are in this, you cannot distinguish these two particles. These two paths cannot be distinguished. And therefore, they two paths, the red path and the green path, they should interfere. Right? So this is the two particle interference effect. That was pointed out by Farlow in 1961. So this intensity correlation truly contains some two particle interference phenomena, and therefore it's a quantum property. So now let's look at this interference. These two, red amplitude for red process and amplitude for green process. Green process, you exchange two particles, and therefore compared with the red path, the relative sign should be opposite for fermions, but for bosons it should be the same. Okay. So now, performing this intensity interference experiment, we can distinguish fermions and bosons. Because of this negative sign, the intensity correlation is always negative for fermions, but always positive for bosons. Okay, that was the point. So using this now Hanbury Brown and Twiss experiment, we can now investigate many quantum statistical properties of many different systems now. But here, for the reference of my work, I want to point out that for the idealistic Hanbury Brown experiment, it is important to have two ingredient things. Essentially, you should have the well-defined beam of particles and beam splitter. For example, if you replace this beam splitter by kind of Y junction, which is more common in electronic systems, then we have multiple reflection between Y junction and this source. So for example, the spatial correlation is, in this case, the spatial correlation is quite clear in this beam, but here it can also, the final result can also affected by the correlation within the source. So this is important to distinguish. So to have a very good beam splitter, tunable beam splitter is very important. So that's why in the electronic system it's not so obvious. Okay, so I told you that for the Hanbury Brown and Twiss experiment, it's important to have a tunable, well-defined beam splitter. For electrons, it's not so easy, but recently they realized the beam splitter, electron beam splitter, by using quantum Bohr edge state. Quantum Bohr edge state is quite easy to understand. For example, if you apply a very strong magnetic field in the two-dimensional system, then because of the cyclotron motion, the electron motion is rather confined in a circle. But around the boundary, it cannot make a full circular motion, right? Because it is interrupted by the boundary of the sample, so it is bounded. So this semi-classical picture of the bounding motion is actually corresponds to quantum mechanical edge state. So in quantum mechanics, this does not make sense, and fully you have a well-defined string component, the well-defined edge state, localized to the boundary of your systems. But the important thing is that here, it's the parallelity. Electron, because of the cyclotron motion, electrons moves only down in this case. It can never move upward. So in that sense, it's a chiral. So this is important for the beam splitter because it prevents the backscattering. For example, here electrons is injected, but here you have some scattering center, but it can never be backscattered. Either it can go on or it can be transferred to here. So this splitting behaves truly like a beam splitter for electrons. So that was being explored by these two groups. Well, actually, this group only. This group used a slightly different one, and they tested electronic Hanbury Brown and Twiss experiment. They had this negative sign indeed. Unfortunately, this is probably one of, as far as I know so far, this is the only example, the only example of electron beam splitter so far. Unfortunately, this electron beam splitter cannot be used for Cooper pairs because here to get such an edge state, you have to apply a strong magnetic field, 10 Tesla. And that immediately destroys the Cooper pair. I forgot to mention the Cooper pairs is a pair of the up electron and down electron. So if you apply a strong magnetic field, it flips, and therefore the pair is broken. So this system cannot be used for beam splitter or Cooper pairs, unfortunately. So we have to think about some other option. So to think about some another option, now I thought about some new state of matter, the topological insulator. So here I just give you one example. So spin-orbit coupling. This is a textbook example of quantum mechanics, right? In isolated atom, we have spin-orbit coupling because of the relativistic corrections of the electron motion, right? So it is proportional to this. But if you have a regular array of atoms, then this is an electric field basically by the atomic ions, and therefore if you put them in a regular array, they are cancelled pretty much. So for the free electrons, this spin-orbit coupling, they do not feel the spin-orbit coupling of the atoms. So there is, in the solids usually you cannot, it's not so easy to observe spin-orbit coupling. But if you break the inversion symmetry, now the cancellation does not occur. So probably you can have some spin-orbit coupling. And another way to achieve it is that you break the structural inversion symmetry, and therefore like a typical semiconducting quantum well. Here, mercury telluride, one kind of semiconductor, another kind of semiconductor. So then electrons are confined in this region, and the spin-orbit coupling survives against the cancellation of different directions. And in this case, the spin-orbit coupling is described by this simple form, momentum times speed. So in this case, momentum plays a role as an effective magnetic field for speed. Okay. So this is, in condensation physics, this was really celebrated these days because of the spintronics, and here we have experts of this doing. Well, we can go a little bit further. We have a solid regular array atoms, and therefore there is a translational lattice symmetry, lattice translation symmetry. This translation symmetry you can use to identify some quantum number, and let's call this as a wave number, like a plane wave. Of course, the spin can be a good quantum number unless spin-orbit coupling is absent. But if there is a spin-orbit coupling, now the spin directions pretty much depend on the lattice, and therefore you can ignore, you can remove the spin quantum number. It cannot be a good quantum number, and therefore the total spin state is described by momentum dependent sum state. In this particular, in some particular problems, it's not important the detailed form, but the spin-orbit coupling still preserves the time reversal symmetry, and it has this form of Hamiltonian. The important thing here is that this Hamiltonian and this Hamiltonian are exactly the same, except for this minus sign. It means there is an exact degeneracy because of time reversal symmetry, the famous Kramer's degeneracy. Right? So now you can identify, in principle, you can solve this eigenstate for each k, and then you can calculate this strange quantity. What is this quantity? This quantity is nothing but the Berry phase curvature. So it's a mathematical quantity, but surprisingly, in this two-dimensional system, this highly mathematical Berry phase term is related to physically measurable quantity, which is the Hall conductance. So Hall conductance is given by this integration of the whole momentum space, and this is well known that this should be an integer. It cannot be an arbitrary number. Whatever the system, how complicated the system is, it should be the integer. And it is a famous topological number related to this topological geometry of this Hamiltonian, and it should be a number. Its number is called Chern number. In condensed matter physics, it is the quantized conductance. And then there is a magic. There is a theorem, which I'm not going to prove here. There is a theorem, as long as this quantum number, the topological number is non-zero, then you should have, around the edge, you should always have gapless one-dimensional edge state. So in the quantum Hall state, it was quite easy to understand semi-classically, right? The bouncing back and forth from the edge because of the cyclotron motion. But here, you cannot make a clear semi-classical picture. Nevertheless, the theorem tells us that there should be gapless excitation, like one-dimensional, true one-dimensional system. In this particular case, the amazing thing is that because of the spin-orbit coupling, upspin always rotates anti-clockwise, and downspin always rotates clockwise, and vice versa. So this, for example, upspin never goes back, and downspin never goes backward. So we have now again some chiral edge state, but because of the spin dependence, we call this as helical edge state, which is in analogy with the photons, with helicity right has a spin up, and helicity minus has a spin down, and it does not have the zero spin mode. Right? So in analogy with this photon state, we call this edge state as a helical edge state. So what's the point of this helical state? I told you that Cooper pairs a pair between upspin and downspin. So you can now sit Cooper pairs here, and then it can propagate along this edge. So we can have a well-defined beam of Cooper pairs. And then we are lucky, then we can also have some beam splitter of Cooper pairs. That's
the up or down, the pairs themselves, they are in the up or down? Or?
Sorry?
So the single electrons are up or down, but the pair?
I don't understand the question.
Here the question is, single electrons are up and down, but the Cooper pairs is composed of an up and down electron.
Yes.
How do you move here?
Split or?
You do break or?
No, you don't have to break. So, okay, just a second. Okay, here. you just put a superconductor, and this superconductor can, the Cooper pairs within the Cooper pair, the superconductor can penetrate go here. And it can, we believe, many people, so far we have been believing that these pairs still have the same property as the Cooper pair inside the superconductors. Right? I'll explain you a little bit detail, slightly, right? So let's go back a little bit. You asked the question too early. Okay, so the point is that Cooper pairs originally they are living in superconductors, inside superconductors. If once they are out, then of course they are broken because they don't have the interaction anymore. Right? Okay, now here I have non-superconducting material in the energy space. So here I draw the picture of the superconductor. Here I have the gap because of the superconducting gap. If you want to break the Cooper pairs, then you have the cost energy. And here that I draw it. So that's the superconducting gap. Here, because it's a non-superconducting, you don't have a gap. Here, blue line, a blue shade means the electrons are all filled. And here it's unfilled. That's a here field, right? So let's suppose that electrons are injected from normal side, non-superconducting side, for example. Here, okay. And then it cannot go here because there's no state in the superconducting state, right? Because of the gap, you cannot put it here. Instead, you make an electron-hole pair, like a particle-antiparticle pair. You take out, and a hole remains. So it's a particle-hole pair. One of these you take, combining a Cooper pair, and then you can enter into the superconductor. This hole remains, and it should go back. Because of the momentum conservation, it should only go back. In the real space, this is an energy space. In the real space, electrons go in, forms a Cooper pair, and the hole is reflected. So this kind of electron-hole reflection is called, it's not like an electron reflection. Right? It's different. It's electron-hole reflection, and this reflection process is called Andreev reflection. But what we want is, we want to extract the Cooper pairs from the superconductor, but you can, if you think a little bit, then it's equivalent to, if you reverse this direction, then it's equivalent to pulling this Cooper pair into the normal conductor. So this is the mathematical description, very convenient mathematical description of extracting or putting Cooper pairs out of superconductor or into the superconductor. Did I answer your question?
I don't know, maybe later on.
Sorry, may I ask you, the momentum of the two particles forming the Cooper pair, isn't this momentum reversed? This momentum reversed?
Yes, Cooper pairs are formed of up-down opposite speed and opposite momentum. But if the Cooper pair is want to move in a certain direction, then it's not exactly opposite. The difference, the middle point is the overall momentum. So
but they are moving somehow in opposite direction, but with some drag.
yes. So if you look at the pair wave function in the real space, then it has moves this way. So it's important. Usually the specular reflection is that if it goes, then it should be reflected that way. But the whole is reflected exactly the same direction. So that means if in mathematical description whole is reflected that way, then Cooper pair is moving either that way or that way. You can trace back the motion of the wave packet of the Cooper pair by tracing the direction of the electrons and holes. So in this case, you are injecting Cooper pairs in this direction. If you extract the Cooper pairs will move that direction.
So to extract a Cooper pair, you have to send a hole in?
Yes, yes, right, exactly. Okay, so I think I've got all ingredients. Okay, here I have helical edge states for the guide, kind of wave guide for the Cooper pairs. I put superconductor. It behaves like a source of Cooper pairs. So Cooper pairs is come in and move along this direction, right? So remember that this electron goes this way and this electron goes that way, but Cooper pair moves that way. The reason is that the wave packet, we are looking at the wave packet. Even though with the well-defined momentum it behaves like that, but the wave packet, if you form the wave packet, it moves along this direction. So I have to put an additional...
That's a electron, or is it an electron hole there?
No.
When you get outside.
It's equivalent, electron pair. So when I say Cooper pair wave packet, it's an electron-electron pair. But usually I will describe in terms of electron hole pair.
Okay,
but they are equivalent.
So what I understand is that the Cooper pair doesn't have an up or down. It behaves like one of them because of its momentum. But why does it choose to behave like the red one and not like the blue? That's what I don't understand.
Oh no,
it's composed of both of them.
It's a singlet, so you cannot really tell if this is really down or if this is up.
It chooses to behave like one of them, but the one that it chooses to behave like is the one that it has the same momentum with?
No, these two electrons should have opposite momentum, but slightly offset. As I said, if two...
How does, what makes the Cooper pair choose one of the two?
Momentum offset.
The momentum offset, okay.
So, right, this is already more. So the Cooper pairs is formed for up k. One of them should have this, minus k and down. If you form a Cooper pair with exactly opposite momentum, then Cooper pair stands there. It does not move. If you want to move those Cooper pairs, then you have to put some momentum offset. This momentum is the direction of the Cooper pair motion. Right, so this is the source, but I need this an additional path because it's an helical edge state. Edge states cannot be terminated in the middle. So if you want to remove some additional unwanted phenomena, then you have to put some sink of the electrons. Okay, now I have everything at my hand, so I want to put them together and want to do some Hanbury Brown and Twiss experiment. Let's start with the easiest one. So everything is normal now. Everything is normal, and I applied here only the voltage here. So basically, this is the only source of the electron. So it's a normal electron. So down, you cannot inject the down electron to here because down electron always moves in this direction. So no, sorry, up electron cannot inject. Only the down electron comes here. Either it goes that direction or in this direction. But it cannot never go back because of the Kramer's degeneracy. So again, this thing using the helical edge state behaves like a beam splitter for electrons. So we have now two required things, well-defined beam of particles and also beam splitter. Okay? But here is a normal electron. But okay, so there are two possibilities: either go here, either go here. It's the typical Hanbury Brown experimental. So if you measure the intensity here and here, the current correlation, and then you can measure the statistical property of this electron from C hat. Right? So to do that, to describe this thing rigorously mathematically, I have to identify the scattering matrix. All the mathematics is provided by, for photons, Glavo already did it for many years ago. And for electrons, Beauty calculated all the details. So I just followed it. And here, in quantum optics, they usually calculate this G2 correlation function. But we, because of the experimental restrictions, we usually calculate the zero frequency Fourier transform of G2, which is we call the shot noise. So we always calculate the shot noise and measure experimentally the shot noise. This is just current correlation function. Okay. Alpha means the different detectors. So I calculated using this thing, and this is a non-interacting theory, and you can calculate quite simple. And in this case, all normal, the current is given by that, right? The probability, this is transferred to here is the probability R squared. So it's quite clear the current should be proportional to T squared, go through it. Current to B, it should be proportional to the tunneling property R squared. And as we expected, the cross correlation A and B is minus and exactly proportional to I, 2EI. This is important, 2EI. For a non-interacting free electrons, it's 2EI times this quantity, the cross correlation.
What about D?
Oh, D is, it presents only because the helical edges you cannot terminate in the middle. So you cannot avoid this, but it does not play at all. Current is zero, noise is zero, it's just, it doesn't play anything. But I cannot remove it because the helical edge state cannot be terminated. You cannot remove from here somewhere. But anyway, you need this. But if you apply your same bias voltage here, then it does not play any role.
But it's not equivalent to the second entry of the beam splitter in optics.
Second.
So also in optics, when you have a beam splitter, you have two input actually. One is vacuum, but still is there when you have two outputs. And the D is not equivalent to the second input of the beam splitter in optics.
No, probably there is another setup we can compare. Probably let's go back, come back to that question with that, right? Because I have another setup too. Right. Okay, so in the normal case, it's quite simple. Now let's go to the main point. So I replaced one of them as a superconductor. So I applied bias voltage only here. So basically, the Cooper pairs are injected only from this one. So these three are effectively just detectors. So it's here for mathematical description, A is the undraft reflection probability here at this interface. But anyway, so you can think of this as some phenomenologically. So Cooper pairs, I told you that it follows this helical edge states. It can either go along this because there is a pair of edge states. You can this injected Cooper pairs can follow this way, or it can turn into the upper edge and go into that way. Okay. So now instead of single electron, we have Cooper pairs. Cooper pairs either go that way, either that way, and we measure intensity correlation between A and B. Cooper pairs, many believe that, and I also believe that to some extent behave like a boson. If you measure the partition noise of bosons, either this way or either this way, then intensity correlation should be positive. Probably not as positive as a pure boson, but probably some reduced positivity, maybe. That was my expectation. But there is a third process actually here. Cooper pair can split because it's not a true bound state, and therefore they can split quite easy. One electron go here, the other electron go there. So this process is actually quite relevant. This recently by these two groups, Basel and French group, the ENS in Paris, they explicitly measure these Cooper pair splitting probabilities. So using this quantum dot. I will not go to details, but using this quantum dot and the strong electron-electron interaction, they focused only on this process. They ignored this process somehow. They suppressed this process. So using this, then electrons are always go together. If you find the electron here, you always find the electron here. So the intensity correlation should be positive. And indeed, they, sorry, I was fascinated by this cartoon, and instead of data, I put this cartoon. Sorry about that. But the data showed clearly that this should be positive. Sorry. Maybe you go to this website, then you will find the data. Sorry. But anyway, so now, we have to take into account the three all possible processes. But as I said, these two processes contribute, naively thinking, contribute positive correlation. And this split up, then they always appear simultaneously, and therefore I would expect positive correlation. Right?
Yes. But once they are split, how can blue ones still follow? Then it goes against its own path. So
I told you. Right? So here, if you this offset, momentum offset, it goes in here. Okay, so it goes here. If this electron has a pure, well-defined momentum k, then of course it moves that way. But we are talking about the wave packet of the pair. So the wave packet of the pair moves that way. The way you trace is that you reverse the direction of the electron or hole, one of them. Then you will follow the...
Even when they are split? Yes, it was open.
Yeah, it's a bit confusing because you have to switch back and forth this electron and hole. Okay, this is the result. This result was calculated by means of microscopic description of electrons and holes. And I have this minus. Not only minus, it's minus times 2EI. That's exactly the same as the free electron case. This was really drive me nuts. It was really difficult to understand. So I think now I have an explanation. So let me try. There are three possibilities, of course. The first, probably I made a wrong calculation. That's obvious. Secondly, probably my setup has some artifact. Right? Probably, as you pointed out, probably D, this additional pad D, doesn't it play a role? Well, third, maybe we can provide some good interpretation of the result, then probably it's okay. So let me, sorry? Something? Okay, so let me provide you two interpretations. I believe my calculation is correct. All right, so, okay. In terms of, because Cooper pair motion is a bit confusing, let me describe all things using this electron hole picture. So, electrons are injected from A, here down here, can go here and reflect it as a hole because of the boundary, unwrapped bounds reflection, and here. And now it has two choices, either go down or either go up, right? And if the particle is injected from B, it goes to superconductor and reflects back. And here it has two choices, either here and here. Now let's think about the two-particle interference. Electron A, the electron, up electron from A, up electron from B, we have two sources. And now in this case, the whole down hole goes back to A. Down hole goes back to B. So this is the, here I summarized. From A to B, A. From B to B. But these lower processes, up electron from A, up electron from B, the source is the same, but destination is opposite. It goes to B hole, and B electron goes A hole. But of course, these holes, two holes, you cannot distinguish each other. And therefore, you have to add up these two amplitudes instead of probability. But these amplitudes should have a minus, because what you exchange here is these holes. The holes are just like electrons are fermions, and therefore you should have minus sign. This minus sign, exactly the same reason you get this negative correlation of electrons in electronic Hanbury Brown and Twiss experiment. So now I believe that negative is kind of natural. So what's wrong with this picture? Here everything was in terms of probability instead of amplitude, right? Because we have some different amplitudes which cannot be distinguished, so we have to add first amplitude instead of probability. So that's what we made a mistake, I think, here. So there is another way to interpret. Let me finish it in 2 minutes. Okay, this is probably. Okay, let's take a look at this. Focus on these two processes. Electrons come here. Now holes either go here or these here. These electrons, 100% reflected by a hole as a whole. It never other possibility. So it is noiseless. So you can safely remove this one. And then the whole process is just to describe a whole motion. Holes either go here, either go here. It's just a partition of the hole. But a partition of fermions, it should be negative. This process as well. But these two processes, you cannot worry about the interference because they are distinguished. So again, partition noise of holes, negative. Partition noise of another hole, negative. So overall, negative. That's my interpretation. Well, unfortunately, well, not unfortunately. Well, before there was some additional proposals by several groups, especially this setup was by Marcus Budico, like superconductor and quantum chaotic quantum dot and normal two leads, and they calculate this intensity correlation here. They observed a positive correlation. So what's wrong? Okay, I will not go to this because of the time. Let me just point out that my interpretation, why we have different results. In my setup, I had true beam splitter. In their case, they had multiple reflections. Okay. So intensity correlation is measured according to the Bain's interpretation. Intensity correlation here is another measure of the spatial correlation. But in this case, with well-defined beam splitter, spatial correlation is the correlation in the beam, not source, right? Because already they are out. But in this case, the zero frequency sham noise is the sum of the all time. So it has non-trivial contributions of, for example, the spatial correlations here. and the time difference is that long. And then it measures also the correlation within the source. So I think that's why they have positive interest correlation. They all use this Y junction, kind of Y junction, and there are multiple reflections. And that's what I believe. Okay, thank you for.
We already had 9 questions during the talk, but maybe we have some time for 1 or 2 short questions or comments, please.
I don't understand. I mean, a pair needs the superconducting medium itself to be defined, isn't it? So when it comes out, is it that pair? How can you study the statistics of that?
I'm not sure I understood the question. Sorry, can you repeat it again?
You are trying to study the properties of an object, which is the pair. Yes. But a pair is only a pair when it's inside the medium.
Yeah, I mean that's that's a good point. Yes. So the question is that if you want to investigate the statistics of Cooper pairs inside the Cooper pair and the superconductor and outside the superconductor, that's quite a big difference. But you know, it's not so obvious because in the unwrapped reflections, if you have, so these Cooper pairs are already out of the superconductor, but they have pretty much, still have pretty much information about the superconductor. For example, the phase information of the superconducting order parameter and so on. And these, unless there is some strong impurities, these kind of Cooper pairs will believed to behave like mostly the Cooper pairs inside superconductors. That's many people believe, including myself. But the quantum statistical properties investigated in my setup probably point out that probably there might be the case. I don't know. Yes, that's a very good point and a deep question. Yes.
Now you have extra holes.
Extra
holes.
Extra holes.
You have more particles in the strip.
No, I took into account. I didn't take into account the interactions, but I have another project, and there I calculate the interaction effect, and does not really affect qualitatively.
Okay, let's thank the speaker again.
Should be on your side.